Hello. So in this video, we're going to be talking about the even property of functions. And really, even before we jump into that, we're going to be talking about symmetry. So let's take a look at a function. So here we have our nice sort of classic parabola shifted down a little bit. The type of symmetry that we're interested in, from a technical standpoint, this is called axial symmetry. So this is the sort of symmetry that you might have been sort of introduced to in geometry when they're like, if you have a thing and you could fold a piece of paper and it matches up, that's axial symmetry. And it's so named because you have some axis, some line that goes through it that you could fold that paper and have it sort of match up. So in our case, we can go across the y-axis in particular, and this thing becomes the same shape, right? So if we go sort of back and forth, we can flip this thing and it'll sort of just spin in place and become the same thing again, right? So spinning around that y-axis 180 degrees gets us exactly the same shape. So in order for the symmetry that we want to be this sort of even property that we're going to be talking about, we need it to be axial symmetry, but we need that axis, the thing that we actually are going to spin it around, that has to be the y-axis specifically, meaning that even if we took the same shape and moved it, right, if it's the same shape, it should have the same sort of symmetric properties in some sense. But if I move it to the right, this is no longer an even property type of symmetry, because if I tried to spin it around the y-axis, I wouldn't get the same thing back because I've moved that line of symmetry, right? So I moved the line of symmetry to the right a little to get that A, and because of that, this is no longer sort of the same kind of symmetry that generates this even property bit, okay? So we're being really specific and kind of restrictive when we talk about even function property, but there's a good reason, which is what we'll see in a second here. So back to our sort of blank canvas version here. The reason why we care a lot about this y value, or the y-axis, and how it sort of is the axis of symmetry, there's two ways of looking at this. We're going to start with geometric. So if I drew only from the y-axis out, right, again, assuming that it was that sort of first shape that had that even property symmetry we're talking about, just knowing half of this graph gives me the other half of the graph, because I know that it has to be sort of the same thing if I fold it along that y-axis. So even if I have just this sort of one side part of it, I can create the other side because I know it has to match up, right? So the points to the right of the y-axis, these are the same ones as we would get going to the left of the y-axis, ignoring the fact that the x value would sort of switch values, right? So the y value going to the right is the same as the y value going to the left. And in fact, if we think about this as some xy point somewhere on that graph, like anywhere on the right side of that graph, if I look at the left side, well, I should also have the point negative x, right, going the other, that sort of left the other same amount, but I should have the same y value. So xy being on the graph means that negative xy is on the graph. So sometimes, right, the letters are not necessarily helpful, although it gets the point across that this happens for any point. But as a concrete example, if we looked at the point 2, 1, because that's on the right-hand side, I know that if I went the other direction, so I went to -2, I'd also have to have a y value of 1, right? So this tells me that if I have 2, 1, I have to have also -2, 1. And sort of an important thing here is that I picked the right-hand side sort of arbitrarily. Here, what I'm saying is we can flip the x value, meaning that we can use the same size, but in the other direction, we get the same y value, but that doesn't care whether the original x value was positive or negative, right? So if instead I started with -2, 1 and I'd know, okay, well, if -2, 1 is on there, then -2 or +2, 1 is also on there. Right, so this is the sort of geometric version of this even property. It seems a little weird to care about this. It turns out to be incredibly useful in so many places, especially in calculus, but in lots and lots of places, sort of shockingly so in some cases. But the reason why we care very specifically about it being the y-axis is actually for the analytic version. So now that we've seen what's happening, I can give the definition, which includes that analytic version. So math speak, right? The crazy talk version. Definition of our even functions. So if we have f from r to r being a function, we say that f is an even function if for any x in r, f of x is f of negative x. So in human speak, what that means is if we sort of have a nice function, just a function that's sort of defined with real numbers and not some craziness like shapes and stuff, and we know that that thing is even, then what that means is if we plug in a value and we plug in the negative of that value, we get the same thing. And so the takeaway is usually this last little equality. This is usually what people sort of take away from this definition. So the key idea is that if we go the same distance left as we do right from the y-axis, right? If I go some x distance, say in the positive direction, and then I flip that direction, so I go to the negative, but that same amount, I'm going to get the same value, right? That equality is saying the output, the f of those things, is the same. So going the same distance left to right from the y-axis, that's where we need it to be the y-axis. So going that same distance, we get the same y value, okay? So when somebody thinks, when you think even function or somebody says even function, this is the sort of takeaway that you want. This f of x equals f of negative x. That's what you want to have pop into your brain, okay? All right, so what do? We introduced this idea of the even property. We talked about it sort of geometrically initially, right? We talked about it as this symmetry and how we can sort of deduce what half of the function is by knowing what the other half is, right? If we knew, say, to the right, what part of it, sort of what the function looked like, we can mirror it to get the left side. But there's nothing special about the right side. If we knew the left side, we can mirror that and get the right side, right? So the whole idea here is that you can sort of flop back and forth. And that gave us the analytic definition, which is if you go in either direction the same amount from the y-axis, you get the same value. And that's why we need that axis of symmetry to be the y-axis, so that lines up. Okay? So that is that.